Alrighty, lads and ladies, welcome back to Calc 2. We are like ankle deep in the waters of integration theory. So today we're going to just continue submerging. We'll get up to our knee. We ended class last time having looked at a few integration by parts problems, stumbling across one that seemed like a pretty natural IBP thing. It led to a looping integral. Maybe 10 seconds, sorry. If one thing, it's the other. We drugged the puppy this morning. We gave him some Benadryl to get him to shut the fuck up because he's been just absolutely insane for the last like 4 days. So he's chilling on the couch, chewing on God knows what. But as soon as he calms down, the cat just starts vomiting all over the dining room. So, you know. What was that? Integration theory, ankles, knees, toes. How about a dog cam? Let's do that. Yeah, looping integrals. We met our first looping integral on Wednesday. And I have a feeling, I know that the first time I saw those, my brain kind of slowly melted and dripped out my ears. So I think it's probably worthwhile to look at one or two more of those. Let's do the thing. This is MAC2312, section 004, that is Calc 2. And today is the 10th of September, 2021. Excuse me, I'm sorry. Today we're going to look at more integration by parts. Which is section 7.1. And we're also going to look at trig integrals. So there's really two little things I want to do with IBP before I wander away from section 7.1. First thing I'd like to do is show you an alternate proof. Now I showed you the kind of standard proof of the integration by parts formula the other day. There is a proof of the definite integral version that is just a picture. So of course, the IBP formula says that the integral of u times dv is equal to u times v minus the integral of v times du. And if this is evaluated from a to b, then all of this is evaluated from a to b, from a to b. The kind of trick here is to think of the UV plane. I'm going to do my best to remember this. And sort of think of some curve. And then to consider this rectangle. If I'm thinking of this curve as it's drawn here, as we're looking at it here, then v is a function of u. And if I'm thinking of things like this, then u is a function of v. The area in here this would be the integral of v du. And I'll see if we can fiddle with bounds to get the precise statement. So, right, just like you think of the integral of f of x dx as being the area under the curve f of x, here this is the u-axis, and y and f of x are the same thing. So like v and f of x would be the same thing here because this is the v-axis. On the other hand, if you approach this thinking of it like this, then I can think of this area as being the integral of u dv. And all of this, a generic point on this curve would be like u comma v. So this is your u and this is your v. So just by comparing the areas, clearly the purple plus the blue is equal to the rectangle. So you get the integral of u dv plus the integral of v du is equal to u times v. And really, as I've drawn it here, we're going from like 0 up to u in the one guy and 0 up to v in the other guy. So to fiddle with the bounds here would require a little bit of love to actually get the exact statement here. But I can show you first that this rearranges into the regular IVP formula. Just by subtracting that other integral over. And then a link here I can give you with the details to all of the which will show you the details. Better picture proof. This is it. How fast can we do this? There we go. Here we are. Yeah. So if you're integrating from like u1 v1 up to u2 v2, you're integrating along this curve, and you think of this as your u-axis and this is your v-axis, then this would be the integral of u dv done from u1 up to u2. The darker area up here would be the integral of v du done from v1 to v2. And then the total rectangular area here, the dark gray and light gray area together, would be u2 u1, or sorry, u2 v2 minus u1 v1. And that's precisely what this piece would be. So I invite you to take a look at this and read the discussion here. To be 100% detailed on this would require a little bit more time than I want to spend. And of course, the proof down here is the one that we're familiar with. It's the one we did in class the other day. But I really encourage you to take a look at this and the links and the discussion here. It's a good thing. Also, Stack Exchange in general, this website is badass. Research mathematicians use this all the time. It's really, really good stuff. So if you're trying to ask math questions or you want to search about something mathematical, Stack Exchange is the place to do it. All right. But that's really the picture proof, right? This is it. This is the integral of u dv, this is the integral of v du, and together they give you u times v. All right. I want to do one more looping integral before we leave section 7.1. So that's what we're going to do next. We did the e to the negative x cos x integral on Wednesday. And that wasn't too bad, right? You guys remember how that went? You run integration by parts twice. Then your original integral shows back up. And now you've got basically an algebra equation you can solve for that original integral. You've got your original integral is equal to some shit minus your original integral. So you add it to both sides and victory. This is going to be similar, but the integrand is going to be very different, and you're only going to need one run of integration by parts here. The particular guy I'm thinking of secant cubed. Integral of secant cubed. Now I know the secant function is very rarely any calculus student's favorite trig function. And I know trig functions are very rarely any calculus student's favorite family of functions, but the section we're going to be moving into today is all trig functions, right? All trig integrals. So this is a nice kind of segue because it happens to be an integration by parts problem. All right. Some prerequisites for this. One thing I am going to have to use here is the integral of secant itself. Does anybody remember the integral of secant or how this is done? Oh, yeah. Wow, nobody's Calc 1 class did this? It's supposed to be done. Anyway, so the way you integrate the regular secant function is by multiplying by secant plus tangent over secant plus tangent. It's a very sneaky trick, and nobody goes through this every time they need the integral of secant. Then you distribute the secant upstairs and you get secant squared x plus tangent x. And then the bottom, sorry, tangent x, secant x. I should have written secant tangent anyway. And then downstairs you still have your secant x plus tangent x. Is this ringing any bells? Does anybody remember this at all? I'm getting nervous here, so I'm going to do something quickly. Give me a react in Zoom, right? A thumbs up react or any sort of reactions. Just look down on that control bar for your reactions. Give me any sort of react if you've seen the integral of secant before. Okay, just 2 people. That's good that we're doing it then. This is supposed to be done in Calc 1, section 5.5. It's like the classic problem. So you multiply by secant plus tangent over secant plus tangent, and then you stare at this for a minute and you realize secant squared, secant tangent, or tangent secant, that's shit I've seen before. I know those. Secant squared is the derivative of tangent. Secant x tangent x is the derivative of secant. So you make the substitution. I'm going to use the letter z. Z equals secant x plus tangent x. Because then dz is, what's the derivative of secant? It's secant tangent. It's the derivative of tangent, that's secant squared. And this is exactly what your numerator is. They're in different order, but it's the same thing. So you make this substitution. This integral becomes 1 over z dz. Which is the natural log of the absolute value of z plus c, which is the natural log of the absolute value of secant x plus tangent x plus c. So this is the sort of, in order to do the looping integral, secant cubed, you got to remember the integral of secant. And most people memorize this one. Most people memorize the integral of secant is the natural log of secant plus tangent. Just like you memorize your other standard trig integrals, right? Nobody's going through a procedure to remember how to integrate cosine. You just remember, oh shit, integral cosine is sine. Nobody goes through a procedure to integrate secant squared. You just remember, oh, integral secant squared is tangent. Same thing for regular secant. You just remember, oh, the integral of secant, that's the natural log of secant plus tangent. All right, so since only 2 people had seen this, I need to encourage you guys or remind you guys to commit this shit to memory, right? This is one of your standard antiderivatives that you need to know. Okay. So let's tuck that in our pocket and see if we can attack the secant cubed integral. Unfortunately, the Lipet rule does not help us here because there's only trig, right? Logarithms, no. Inverse functions, no. Polynomials, exponentials, no. Trig, yeah, but everything is trig. So that would leave me with just dx as dv, and that really doesn't help. What will help here is remembering that secant cubed is secant times secant squared. And I know how to integrate secant squared. So if I pick this piece to be dv and this piece to be u, then I can at least proceed in a nice way. But the integral of secant squared is very nice. What is the integral of secant squared? Said it a second ago.
Tangent.
Very good, it's tangent. Yeah, thank you, Frank. So what I'm going to do is I'm going to run IVP, choosing this piece to be dv and this piece to be u. So here's my IVP table. U is the secant of x. dv is secant squared x dx. V then, as Frank just reminded us, is tangent x. The integral of secant squared is tangent, is the derivative of tangent is secant squared. And du, the derivative of secant, is secant x tangent x. So du is secant x tangent x dx. That's our little IVP table for this problem. And then I apply the integration by parts formula. It says the integral of u times dv is u times v secant x tangent x minus the integral of v du. Now that's tangent times secant tangent, which is secant x times tangent squared x dx. I'll tell you now, in your homework lies this integral, secant times tangent squared. You handle this one pretty much the same way as you handle the secant cubed. You can either turn this into a secant cubed using some trig identities, or you can attack this directly using integration by parts. But this integral is in your homework on its own as its own problem. And you need to solve it similarly to how we're doing the secant cubed. It's a looping integral. All right. Since here we're starting with secant cubed, my goal is to make secant cubed show up again. Right? That's how this looping thing works. That's why it's called looping, right? Because you get your original integral back and then you can add it over or whatever. Does anybody see a way for me to make a secant cubed show up in here? Think trig identities. This is one of your fundamental trig identities, right? It's the Pythagorean identity for tangent and secant. You take sine squared plus cos squared equals 1 and divide everything by cos squared, you get tan squared plus 1 equals secant squared, this guy. Which means that tangent squared is the same as secant squared minus 1. And we will be using these trig identities up, down, left, right, every which way over the next few days. So it's very, very important to remember them. If you have trouble with trig identities, see the review material in the modules, or come to me for help. I can give you lots of different ways to remember these that you must remember. All right, so that tangent squared, I'm going to replace by secant squared minus 1. We do so in parentheses. All right, because secant here is multiplying the tangent squared, which means secant here needs to multiply all of secant squared minus 1. So these parentheses are not optional. Next, I'll distribute this over these two terms. And that'll give me secant cubed x minus secant x dx. And in this next step, I'm going to do two things. I'm going to bring this negative into the integral. That will make the secant cubed here negative and the secant here positive. And I'm going to split up the integral. Just basic algebra. So I have secant x tangent x minus the integral of secant cubed x dx plus the integral of secant x dx. And now we're home free. What is good about this? Somebody tell me, why is this line being equal to the integral of secant cubed a victory statement? I understand it's Friday morning, but does anybody see anything in this line that might be relevant or useful to the problem?
You can add the secant to the power of 3 to the other side.
Very good. Here's my original integral showing up again. So we can add this over. Now there's a tiny catch, right? The tiny catch is that there's still this integral of secant over here, but do we know what the integral of secant is? Yeah, it's the thing that we did a second ago. It's the thing that we did before we started the integral of secant cubed, right? So recall. So we're going to add this to both sides. All right. Maybe it will help if I rewrite this like this. All right. Integral of secant cubed x dx equals secant tangent minus integral secant cubed. So when I add that to both sides, two times the integral of secant cubed x dx equals secant x tangent x plus the integral of secant x dx. The integral that remains on the right-hand side is a known quantity. It's the natural log of secant plus tangent. And then divide by 2. And we need to write a plus. So these looping integrals are called that precisely because you work with them for a while and then the original integral shows back up. The problem loops. Once you get to this stage, you can say, oh, my original integral is equal to some shit minus my original integral. So I'll add that over, giving me 2 copies of that original integral equals just the shit. As long as you know what this shit is, then you're done. Victory. Now, if this said minus 2 integral secant cubed x dx, then when I add 2 of those over, I would get 3 times the integral of secant cubed. if that said -1/2 integral secant cubed x dx, when I add that over, I would have 1 plus 1/2 is 3/2 integral secant cubed x dx. So constants aren't going to give you any trouble here. And we could insert various constants in here, like secant cubed of 5x or something like that, which would result in some other constants showing up here. All right. So you've seen me do 2 looping integrals in class. You've seen the damped harmonic oscillator, and you've seen the integral of secant cubed. You need to practice these. There will be looping integrals on the test. You will have to do this procedure on the exam. Before I wander away, I wanted to show you a nicer graph of the damped harmonic oscillator, and then we're going to start talking about trig integrals. We may or may not have time to get all the way through the trig integral stuff. That's okay. So we looked at last time y equals e to the negative x cos x. And unfortunately, this damping term, the e to the negative x, damps so quickly that it's hard to see what's going on there. But I wanted to show you just a slightly less aggressively damped natural harmonic oscillator, damped harmonic oscillator. So here's that behavior, right? Regular cosine stuff is just getting squished down really fast. This is the thing from last time we looked at. Just want to show you that. All right, trig integrals then. All right, this is an example of a trig integral, obviously. Thankfully, secant cubed, odd powers of secant and odd powers of cosecant are the only trig integrals that you have to manage that way. All the other ones can be attacked much more directly, much more cleanly through a combination of trig identities and U substitution. Basically, we're going to break all possible trig integrals down into kind of 2 families. It is a nice fact. Any rational combination of trig functions can be split up into an expression whose individual terms are like some power of sine times some power of cosine and or some power of secant times some power of tangent. So you give me some nasty mess of all sorts of trig functions, you know, raised to powers, multiplied by each other, added up, divided by similar looking things. Any trigonometric polynomial, even divided by another trigonometric polynomial. We can always split those up into things like this and things like this. It may take a great deal of work, just algebraically, but it can always be done. So in this section, trig integrals, we're going to focus on handling stuff like this and handling stuff like this, because we know that we can take any nice, reasonable combination, rational and trigonometric polynomial over trig polynomial, any rational combination of trig functions and split it up into things like this. Next, outside. Go. 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 So we want to learn how to integrate powers of sine times powers of cosine and powers of secant times powers of tangent. Those are our goals. These are the 2 big families. So first we're going to deal with integrals of the form integral some power of sine times some power of cosine And these we split up into cases, depending on whether the power of sine or cosine are odd or even. I think the best way to kind of teach you this is through examples. So let's look at one or two examples here. I want to integrate sine x times, let's say sine squared times cosine x dx. This is a problem that I think you may have seen on your very first homework set in this class. Anybody know how to do this guy? I remember. I know it's Friday. I know it's early. I do need you guys to show me you're paying attention though, so help me out a little bit. Any thoughts on this? No wrong answers, just tell me what comes to mind.
Could you substitute the sine squared?
Almost, definitely a little substitution would be nice. If I sub for sine squared, then the differential is going to be a little complicated, right? Because I got to use the chain rule. So even a bit simpler than that. If I kind of think, what is my inner function here? The squaring function here, I can think of this as the sine being the inside. And then the du is just cos x dx, which is perfect because I've got that sitting right there. Right, this piece is du. So this integral will just become the integral of sine squared, that's the integral of u squared, times cos x dx, well, that's just du. So that's 1/3 u cubed plus c, or sine cubed x over 3 plus a constant. This same basic spirit works anytime there is at least one odd power in the sine cosine integrals. All right, so if at least one of the powers is odd, then you can do this same shit where you just straight up substitute for one of the guys. So let me look at something like sine to the 5th x times, I don't know, cos squared x dx. As these powers get larger, things look a little more and more intimidating. But the basic ethos is still the same. Here's the idea. Let's look at this one. One of the powers was odd, one of the powers was even. I ended up using the function from the odd powered piece in my differential. And I ended up subbing for the function that was raised to the non-odd power. I can do the same thing here, but because the odd power is a 5, if I sub u equals cos x, du would be negative sine x dx. That's only going to eat up one of the 5 sines here. So let me kind of try to just naively run the same thing. I'm going to sub for the non-odd guy. Like here I had sine squared, sub for sine. Here I have cos squared. I'm going to sub for cos. Du is then negative sine of x dx. So this du is going to eat up one of these sines. Does everybody see that? However you choose to think about it, if you like solve for dx and plug in, then one of the sines would cancel. So the result is going to be negative integral. I don't like writing this, but I'm going to write it. Sine to the 4x times cos squared is u squared. Maybe I'll just leave that as cos squared x. And then du. So all I did is plug in for the differential. Yeah, we're substituting, yeah. So all I've done here is plug in for the differential. Dx is -1 over sine x du. So this power here went down by 1 because this term canceled one of the signs. And also this negative shows up. Now, why is this nice? Well, cos squared x, that's just going to be u squared. The sine to the 4 of x is a problem, though. We need to get rid of that. Here's how you get rid of it. So you've got negative integral. That sine to the 4, I'm going to think of as sine squared of x all squared. And then I've got my cos squared x and my du. So this is negative integral. Sine squared is 1 minus cos squared. I said you need to know those identities, right? Now, I don't like the way I'm doing this because we're mixing variables. I've got x's and du's floating around. That's fucked up. You know, we really can't do any integration here or here. But I'm just doing it this way so you can kind of understand the motivation. And I'll do another example where I'll show you kind of the workflow as I would normally do it. I've gotten rid of all the signs. It's all cosines now. So now I can say, okay, this is negative integral 1 minus u squared times u squared du. And at this stage, I'm done with the sub. So now I can start thinking about how to actually proceed with the integration. This is a nice thing to do because the resulting integrand is a polynomial. We can always integrate polynomials. So this is negative integral 1 minus u squared is 1 minus 2u squared plus u to the 4. And then this is u squared du. So I'm just foiling this out, right? We've got this power here, this difference raised to a power of 2. So I foil it out. The u squared there is here. It still needs to be distributed. We get negative integral u squared minus 2u to the 4 plus u to the 6 du. And now we're just about done. I guess I'll bring it over here. That's negative u cubed over 3 minus 2u to the 5 over 5 plus u to the 7 over 7 plus c, which is, I'll bring the negative back in. This is negative u is cos x, so this is cos cubed x over 3 plus 2 cos to the 5 x over 5, and then minus cos to the 7 of x over 7 plus a constant. Back up for a minute and give you a second to look at this. In the next example, I'm going to show you my normal workflow, kind of how I would usually do this. But I think if I showed you that first, you'd be a little confused. So the idea here was to kind of take what worked in the last one, in that very simple one, substituting for the non-odd power, so we can soak up one of the odd powered guys in our differential, and then using trig identities. So from here to here, I use the identity. All right, we know sine squared x plus cos squared x is equal to 1. That's your first Pythagorean identity, which means sine squared is the same as 1 minus cos squared So after I just plug in for the differential, I still have these 4 copies of sine x that I need to deal with. I need to get rid of these. I need to rewrite these in a way I can replace them with u's. And the way we do that is by writing sine to the 4 as sine squared squared. And then this inner sine squared, I use my trig identity on. I rewrite that as 1 minus cos squared. Now everything in here is cosines, there's no more sines. So I can swap every cos x for u. And this is the money step. From here, we're home free. This is a polynomial. We know how to integrate polynomials. But the work, as in any u sub problem, the work is in getting rid of all the instances of the old variable. Let's look at one more example, and this time I will show you again my normal workflow, which is slightly different. I'll also complicate things this time by making both of the powers odd. Maxwell. Sorry, guys. All right, so yeah. Let's look at something like sine cubed x times, well, yeah, how about cos to the 5th of x dx. So here both powers are odd. Neither are even. So it complicates things just a tiny bit. But the idea is still the same. I want to substitute, just do u sub for one of the functions, either sine x or cos x. Here I'm going to substitute for cos x. But before I do that, I'm going to rewrite everything here in terms of cos x, with the exception of one copy of sine. So thinking I'm going to substitute for cos, I'm going to take one of those sines, leaving a sine squared here, and just set it off to the side with my differential. So sine squared times sine is sine cubed. I'm just taking one of these 3 copies of sine and setting it over here by dx, because I know I'm going to substitute for cos x. So I know one of these sines is going to get canceled or absorbed, however you like to think of it, by the differential. Then I take the remaining copies of sine and I'm going to rewrite them as cosines. So sine squared is 1 minus cos squared x. And then I've still got cos to the 5th. And then I've got my sine x dx at the end. And at this step, I would substitute u equals cos x. This is how I do this. So I get the integral ready to be substituted into, then make the substitution. I recommend you do the same. Okay. So if u is cos x, this will be 1 minus u squared. This will be u to the 5. And sine x dx is going to be negative du. So I can pop the negative all the way out. And then here I have 1 minus u squared. Cos to the 5 is u to the 5. And sine x dx is negative du. See how clean that is? Then we'll distribute the u to the 5. And then we'll take our antiderivative. So the negative, and then u to the 5 will become u to the 6 over 6, minus u to the 7 will become u to the 8 over 8. This is the step where we add our plus c, because there is no more integral. And then because it's an indefinite integral, we do have to go back to the original variable. I'll also distribute the negatives. This is negative close to the 6x over 6 plus close to the 8x over 8 plus 0x. Okay. Any questions on these last few examples? All right. So if there is an odd power, if you're looking at a sine cosine integral, right? Power of sine times power of cosine, and one of the powers is odd, you're going to solve that problem with u sub. The way you will do that is by subbing for whichever term has the odd power, or if they're both odd. Sorry, let me rephrase that. The way you're going to do that is by subbing for one of them, either sine or cosine, such that the differential soaks up one term of the odd powered guy. If they're both odd, you'll sub for the larger power. If one is odd and one is even, you will sub for the even powered function. The reason this works is because the odd powered function will have one of his guys taken away by the differential, leaving an even power. And you can always write an even power of sine or cosine in terms of the other guy, right? Like here I have sine squared left over. I can write sine squared as 1 minus cos squared. If I had a cos to the 4 left over, I could write that as 1 minus sine squared all squared. So turn it into a sine. So even powers of sine and cosine can always be turned into each other. All right. What if neither power is odd? If you're looking at a sine cosine integral where neither power is odd, that means both powers are even. The simplest case of these is just sine squared or cos squared on their own. If you do not have an odd power, then the substitution thing won't work. The substitution thing only works because you have an odd power, so you can soak up one of those with the differential and then rewrite the remaining even powered stuff using the Pythagorean identities. You could use a Pythagorean identity to turn this into 1 minus cos squared, but that doesn't help you at all. So this is where you'll need the other identities that I mentioned as being critical for this class, the half angle identities. And I think there's a chance, more than a chance, that you either haven't seen these or have forgotten them. So we say cos squared theta is 1/2 times 1 plus cos of 2 theta. And the other one says sine squared theta is 1/2 times 1 minus cos of 2 theta. And before you say anything, they're called half angle identities because the angle on the left, theta, is half of the angle on the right, 2 theta. When you saw these in trigonometry, if you saw them, you probably saw them solved for like the cosine here. So this thing under a square root. And you probably saw them with this as a theta over 2 and this as a theta. Those say the same thing. This is the more useful form. So if there is no odd power, if you're looking at a sine cosine integral and there is no odd power, you're just going to beat the thing to death with half angle identities until you get to a place where you know how to do the integral. So I'll show you here in this nice simple case. Sine squared is 1/2 times 1 minus cos of 2 theta. Oh, sorry, 2x. Confusing myself. Yeah, right. I'm using the variable theta here for a reason, but our variable is x. I can pop out the 1/2, and I'm left with integral 1 minus cos 2x dx. Now we don't need to make any substitutions. If you want to, you could make a tiny little u sub in this piece. I guess I'll go through the details for you here. So this would be 1/2 integral of 1 dx minus 1/2 integral of cos 2x dx. And then in the second integral, you can make the tiny little substitution u equals 2x. Du is just 2 dx. So this means 1/2 du is equal to dx. So this first piece is going to integrate to just 1/2 x. And then here you'll have minus 1/4 from the substitution integral cos u du. So that's 1/2 x minus antiderivative for cos u is sine u. So this is going to be sine of u, which is 2x over 4 plus c. And most people wouldn't write either of these steps. Most people would just jump from like here to here. Little u subs like this, where the differential is a constant, I'm going to refer to these as micro u subs, and they're the sort of thing you want to get good at doing fast. Okay. I'll show you a more complicated problem here in just a second, but first I want to pause. Are there any questions on this one?
Is there any advantage to doing this instead of like making the sign like a U or something?
Oh, well, yeah, this is the only way to proceed here. So like I said, if you don't have an odd power of one of the functions floating around in your integral somewhere, then you won't be able to solve the integral by a regular like u sub, the way we were doing a second ago. If you try to sub u equals sine x in this integral, what happens? This is a good thought. Let's take a quick detour. It's a reasonable thought, right? The inner function there is definitely sine. But if you make u equals sine x, then du is cos x dx. And there are no cosines in here, right? If we try to push this through, sine squared becomes u squared. Dx is 1 over cos x du. And I can't do anything with this. Because there's this mix of old and new variables. Remember back to our very first day when we were talking about what do you do if you've got old variable stuff left over after doing a u sub? You've got to get rid of the x's. This isn't a constant. I can't pop it out of the integral. The integral is being done du now, so I can't integrate 1 over cos x with respect to u. We're really at a bit of an impasse here. Now there are some things you can do. Don't get me wrong. Because it is true that sine squared x plus cos squared x is equal to 1, I can say, okay, well, cos squared x is the same as 1 minus sine squared x, which means that this cosine, as long as everything is positive, which is not a guarantee, would be the square root of 1 minus sine squared x if cos x is greater than or equal to 0, which is, again, not guaranteed. And then I could rewrite this as u squared times 1 over the square root of 1 minus u squared du. But this is not easier than this. This is much worse. And from here, we're really in trouble. In fact, the way you solve this integral, the integral I have at the bottom left here, the only reasonable way to attack this is to go back the other way. You make a special substitution called a trig sub that turns this back into this, and then you attack using the methods I've described in purple above. So there really are no kind of like standard u sub tricks, the sort of thing that we were doing in that first case where there was an odd power that can be applied here to any success. And generally, once you run into something like this, you know you're fucked. It's true that we can force it, but even this is making the strong assumption that cosine is positive, right? When you take square roots here, really you get a plus and minus, and then we're in deep shit at that point, unless we can somehow guarantee that cosine is positive, which it only is half the time. And even if that is true, the integral that comes out is much worse than the integral we started with. So we really don't want to do this. It's a reasonable thought, but there's a good reason why we don't do it. And kind of the ethos, the guiding thought here is, if you have an odd power, then you can do regular u sub stuff. If you do not have an odd power, got to use the half angle identities. It's the only way.
Thank you.
I'm really grateful that you asked. Is anybody else having questions or thoughts, concerns, anything? Again, discussion is good. There's no harm in discussion. 90% of the things I think to try in my own work are wrong. That doesn't mean they shouldn't be tried. We got to try them to understand what's going on. Okay, one more even powered thing. One more sine cosine integral absent any odd powers. The truth is, these are the nasty case, right? If you have an odd power, then things are fairly nice. You're going to set aside one copy of that odd power, substitute for the other function, and just basic trig identities get you there. If you don't have an odd power, the only thing to do is to grind on it with half angle identities. So first, sine squared is 1/2 times 1 minus cos 2x times cos squared is 1/2 1 plus cos 2x, and dx is dx. These things are being multiplied. So in particular, this 1/2 and this 1/2 can both come out and give me a 1/4. And then what's left inside is 1 minus cos 2x times 1 plus cos 2x. And we'll distribute FOIL. And you get 1 minus cos squared of 2x dx. Right, if you FOIL this, the middle terms cancel, the inners and the outers cancel, and you just get 1 times 1 minus cos squared, cos 2x times cos 2x. Right here is the reason why, when I gave you those half angle identities, I wrote them in terms of theta. So I'll just remind you the half angle for cosine. Cos squared theta is 1/2 times 1 plus cos 2 theta. If you let theta be 2x, then you get cos squared of 2x is equal to 1/2 times 1 plus cos of 2 times 2x, which is 4x. So again, kind of the strategic thinking here is after applying my half angle identities, I end up with an integral that contains only even powers of cosine, no odd powers of either sine or cosine present here. So we just have to continue grinding on it with that same identity. Cos squared of 2x, we just discovered, is 1/2 times 1 plus cos of 4x. You want to be very careful with your parentheses here. Big paren at the end is to match this big paren at the start. Then you'll distribute, combine like terms. You'll have 1 minus 1/2 minus 1/2 cos of 4x dx. And 1 minus 1/2 is 1/2. So you've got 1/2 minus 1/2 cos of 4x. And that cos of 4x integral is again a little micro u sub, something you want to get good at doing quickly. The 1/2 will integrate to 1/2 x, or x over 2. The cos 4x will integrate to sine 4x over 4. So you'll have 1/8 sine 4x from this piece. The 1/4 out front is still there. So here we have 1/2 x, and then cos 4x is going to integrate to sine 4x over 4, or 1/4 sine 4x. Together with this 1/2, that makes 1/8 sine 4x. And then you've got your plus. You can distribute the 1/4 if you want. Look at this. So the sine cosine integrals where there are no odd powers, where both powers are even, are kind of unpleasant in this sense that there's not any creative moves. You just grind on it with that half angle identity, or those 2 half angle identities over and over again. I may as well tell you, so micro u subs, you want to get to a place where you can do them quickly. Specifically, you should be able to do these integrals really fast. Sine of ax and cos of ax should be like no-brainers. Integral of sine ax dx, you would substitute u equals ax, du would be a dx, so you get a 1 over a out. And then the integral of sine u is negative cos u. So this is negative cos of ax over a plus c. And the integral of cos ax, same thing. You would substitute u equals ax, du is a dx, so you get a 1 over a out. And then the integral of cos u is sine u. So this would be sine of ax over a plus c. You're free to use these. Without showing the u sub. So on your tests, you're required to show work. These integrals, though, the little u subs that make these go, the things I call micro u subs, you don't need to show that work. And in fact, you should be able to do these very, very quickly. This is something you should just, every bit as quickly as you take the derivative of sine 2x, you should be able to take the antiderivative. And that will make these less painful. Right? If I had to at this step split it up and then make a u sub in this and then recombine, like, fuck that. Right? We know what's going to happen. There's no reason to waste the space. All the other steps here are quite important. So I want you to take a second, look at your work, look at my work, and see if there's anything you want to ask about. last call for questions. Secant tangent integrals are similar to the sine cosine integrals. Before I describe or show you any of the secant tangent integrals, I want to give you the strategy for integrals of the form power of sine times power of cosine. We consider cases. Case the first, one of m or n is odd. So the power of sine is odd, or the power of cos is odd, or both are odd. In this case, you're going to do u sub. What you'll do is take one copy of the odd powered function and set it aside with the dx. He's going to be canceled or soaked up by the differential when you make your substitution. All right, so you're going to do that and rewrite. Well, I'll make this a second step. Rewrite any remaining powers, which will be even, of that function. So, right, if sine was the odd powered function, you would like sine to the 5. You would take one copy of sine and set it over with dx, and that would leave sine to the 4 left. You will take those remaining powers of that function, sine to the 4, and rewrite it. Rewriting remaining powers of that function using the Pythagorean identities. So you're going to rewrite in terms of the other function. So if your sine was the odd powered guy, you're going to grab one copy of sine, set it aside. That will leave you an even power of sine left over. That even power of sine, you'll always be able to rewrite using Pythagorean identities as cosines. Then you will sub u equals the other function. I don't want to say the even powered function because I don't want to confuse. But if sine was originally the odd powered function, you're going to sub for cosine. If cosine was originally the odd powered function, you're going to sub for sine. All right, and that's it. That's how we handle the first case. You will have rewritten all the remaining powers of the other function in terms of this guy. So after you've done that rewriting, say sine was odd, after you've completed this step, everything will be cosines, except for the little copy of sine that you set aside with the differential. That guy will get eaten up by this. It will get canceled or absorbed, however you like to think of it, by the differential du. The other case is neither m and n are odd. In other words, both m and n are even. In this case, you're just going to grind with the half angle identities. Which are sine squared theta equals 1/2 1 minus cos 2 theta, and cos squared theta equals 1/2 1 plus cos 2 theta. The kind of strange thing about these identities is that whether you start with a sine or a cosine, you end up with a cosine. That's convenient because it will turn everything into cosines, and it will also get rid of the even powers. You may have to apply these multiple times, like you saw in that last example, and then micro u subs for the win. So this is how you integrate any power of sine times any power of cosine. All integrals of that form can be managed using this strategy. And the examples we've seen here are characteristic. These are not extra easy examples. They're not extra hard examples. They're normal examples. We have time to introduce the secant tangent stuff, just barely. We've got like some power of secant times some power of tangent. I'll tell you the cases here. If the power of secant is even, we're going to sub u equals tan x. And we'll rewrite any secants left over using the Pythagorean identity.
Professor, it's out of focus, the screen.
Okay. Here we go. All right. So if the power of secant is even, like secant to the 6, then you're going to sub u equals tangent x. Du is going to be secant squared x, which will knock the power of secant down by 2. So if you had secant to the 6, then that's going to become secant to the 4. And then you'll have, u to the n from the tangent and your du over here. The remaining powers of secant will be even, right? Because you take 2 away from an even number, you get an even number. That remaining even power of secant, you will rewrite using the Pythagorean identity, tan squared plus 1 equals secant squared. The other nice case is if the power of tangent is odd. In that case, you're going to sub u equals secant. If the power of tangent is odd, then when you sub u equals secant, du is secant x tangent x dx, one of the powers of secant will go away. That's all right. We'll just have one less power of u. One of the powers of tangent will go away. And if you take one away from an odd power, you get an even power. So the remaining powers of tangent left over will be even. And just like in all these other things, you're going to use the Pythagorean identity to rewrite the remaining even powers of tangent as secants. Okay. So if n, which is the power of tangent, is odd, you sub u equals secant. The differential will consume 1 power of tangent, leaving an even power of tangent. that even power of tangent can be rewritten as secant using the Pythagorean identity. And then you're home free, right? Once you've got all secant stuff, that's all u stuff. So then you just go ahead and do the integral. There's something missing here, right? So it's possible the power of secant is even. It's possible that the power of tangent is odd. It's also possible that neither of those things are true. So the power of secant is odd and the power of tangent is even. That's the shitty case. If m is odd, if the power of secant is odd and n is even, then this is looping IBP. And these can always be turned into odd powers of secant. But however you want to attack it, you can reduce it to like combinations of odd powers of secant, or you can dive in directly using integration by parts. Oh yeah, this is your strategy for secant tangent integrals. Now on Monday of next week, I'll show you examples of these. We haven't gotten to look at any examples of secant tangent integrals. So that homework set that I opened up for you earlier this week, which has both integration by parts and trig integrals in it. I'll probably extend that by a few days. Let me take a look here and tell you exactly where I want you to stop, or exactly how far I expect you to get. All right, so here's your current homework set, homework 3. Plenty of integration by parts. Okay, so what do we got? Lots of sine cosine integrals. This one is a tangent cosine integral. You can handle this. You're just gonna have to think about it a little bit. Is there anything here that you cannot do now? Tan secant cubed. Yeah, so 27, 28, 29, 30, 31, everything after 27. So 27 and on, don't worry about for now. Certainly you're welcome to work them. I recommend you spend some time on them eventually, but please finish up through 26 by Monday. All right, this is set to be due on Monday. I will extend it, but please finish up through 26 at least. All right, it's very important that you don't fall behind on this shit, especially the integration by parts stuff. Since that is already behind us, you must finish that. And then on Monday, I'll look at examples of these sort of integrals. I did see in chat, we wanted to go back to the strategy page for the sine cosine integrals. So let me do that for just a second. This is all in your textbook. In fact, they get more granular about it than I do here. So I've tried to say this kind of as nicely as I can without introducing more notation. But your textbook is very granular about this. So if you want something that's a little bit more detailed than these outline strategies, then you can look there as well. The basic idea for the sine cos integrals is either you have an odd power or you don't. If you do have an odd power, you're going to do u sub. And generally, if you have an odd power, the other power will be even. That's sort of the nice way to think of it. And you u sub for the even powered guy. That will soak up one of the odd powered guy with the differential, leaving only even powers of him, which you can then rewrite in terms of the other function using the Pythagorean identity sine squared plus cos squared equals 1. And then if there are no odd powered guys, then you just grind with these half angle identities. The only weirdness is if both of them are odd. And in that case, sub for the larger guy. That will make life easier. You can get through there either way, but if you you sub for the larger guy, things will go a little smoother. All right, so we'll look at more examples of this sort of stuff on Monday, maybe one more sine cosine integral, but you should be in a place where you can manage those pretty well. And then the secant tangent stuff we will work on quite hard on Monday. Between now and then, you need to make sure you finish through problem number 26 on homework 3. All right, do not just wait to do the homework because I'm telling you I'm going to extend it. Finish up through number 26, please, by Monday. All righty, and we're going to go back to that last page one more time. Here's the secant tangent strategies. Again, real quick, I'll hold here for now. This is broken down in the textbook also. So the secant tangent cases, if the power of secant is even, sub for tangent, use trig identities to make it work. If the power of tangent is odd, sub for secant, use trig identities to make it work. If neither of those are true, that means the power of secant is odd and the power of tangent is even. That means you're kind of fucked. It means you're going to do some looping integration by parts. These tend to be difficult problems. Secant cubed is a case of this, right? The power of tangent there is 0. The power of secant there is 3. Secant times tangent squared is like that. And there aren't a lot of other ones that I can give you because frankly, they get too hard. All right, last thing before I go, about to let you go, I promise. Last thing, if you look in your textbook, you will see this broken down in what I think is excessive detail, but sometimes that's nice. So, plenty of examples. Here's the strategy they give for sine cosine integrals. You know, if the power of cos is odd, then you turn everything into sines and sub for sine. If the power of sine is odd, you turn everything into cosines and sub for cos. If they're both even, then you grind with these half angle identities until you get where you need to go. And what they don't cover here is if they're both odd. If they're both odd, then you could sub for either. I recommend subbing for the larger guy. The secant tangent strategies are in here as well. That's like I said, if the power of secant is even, then you're going to sub for tangent. If the power of tangent is odd, then you're going to sub for secant. And again, use trig identities to make it go. Alrighty, that's where I got to leave you guys for today. So please work hard on those problems over the weekend. Between now and Monday, you need to finish up through number 26. Hopefully you've already started on that, but if you haven't, hopefully this reminds you to do so. And then on Monday, we will wrap up section 7.2 and we will move into section 7.3, which is on trigonometric substitution, which is where we take non-trig integrals and we make them trig integrals, right? Stuff like this, we turn into a trig integral. So that'll be fun. Between now and then, if you need help with anything, reach out, come by office hours, post on the Discord, send me a Canvas message. You know the drill at this point. I will see y'all on Monday.
Thank you.
This PDF, it's a copy of the textbook. So if you have a hard copy of the text, you can look there. You can look in WebAssign. There's an electronic copy of the text there. It's not this PDF. If you desperately want this PDF, send me an email and I'll find a truck it can fall off the back of for you. All right, take care, guys.